Hello everyone, and welcome to today's Optimization Masterclass, Improving Python-based HPC Workloads. Some brief points of housekeeping for you. You will have the opportunity to submit text questions to today's presenter, and all you need to do is to type your questions into the questions pane of the control panel. And you can send in your questions at any time during the presentation, and we will collect these and address as many as we can during the Q&A session at the end of today's presentation. I'd like to introduce you now to our solution architect, Florent Lebeau.
Thank you very much for the introduction. I'm very glad to present this webinar today about the latest feature of our product, ARM-Map, which now supports Python profiling. Among the topics that I would like to cover today, I would like to tell you why Python is becoming increasingly popular in HPC. And I would like to show you a few examples of how you can profile your Python codes today. I will then introduce the ARM Map Profiler designed to profile parallel applications. And I would like to show you the broad capabilities of the ARM Map Profiler in order to optimize your Python-based workloads. So before we start, a few words about Python, and especially why it is becoming popular in HPC. Python is a high-level and general-purpose language created in 1991. It is designed to be readable, indentation is meaningful, and it is used to specify blocks of code. Python is both free to use and open source. It is an interpreted language, and CPython is the most popular interpreter, developed as open source by the Python Software Foundation. It is effectively cross-platform, running on x86, ARM or Power, and OS agnostic. Python is easily extensible. A large number of modules can be used to add features to the interpreter. For example, matplotlib is a popular module among scientists to display graphs or animations and analyze data. These modules can be installed with a Python package manager like pip or conda. So from what we've shown before, we understand that Python is suitable for scripting workflows or prototyping algorithms. But it is also able to execute performant parallel code too. For this, modules like NumPy, SciPy, or MPI-4Py exist. They rely on highly optimized libraries widely used in HPC, such as BLAS laid-back libraries for linear algebra, or FFTW for signal processing. Because Python is can be easily interfaced with other languages like C, FORTRAN, more and more scientific applications rely on Python and its extensions across many disciplines. For example, GPAL for atomic simulation, Phoenix for differential equation, or PyFR for CFD. The easier way to profile a code is probably to use the time module along with print statements to get an idea of how fast your code performs. However, if your code is large, and if you don't want to modify your code, you may prefer cprofile, which relies on deterministic profiling. cprofile collects information from the interpreter to give an accurate picture of the code usage with a fairly low overhead. cprofile will show you the number of calls, the number of time spent in a given function, and the cumulative time spent in this function and subfunctions. If you would like to collect line source information, you will need an extra tool like Line Profiler, for example. Line Profiler requires to decorate a function and use the current prof executable to profile it. You can see this the kind of output here on the screens. It gives you the number of hits of a particular function and a corresponding percentage of execution time. This tool can be installed with pip as well. So you can see that profiling comes with a few challenges and limitations. In particular, because in HPC, applications can be large and complex, with millions of lines of code and bits written in different source languages. You want a tool that is able to be used in a complex workflow without any instrumentation. HPC applications are used by scientists who need to understand performance without digging in the internal mechanism of profiling. So again, you need a tool that is easy to use, usable. HPC users are looking at tools that can provide them with profiling results at large scale, for example, hundreds of thousands of nodes, with little overhead as possible, so that the result describes the application as it is running in production. So here is our solution to their needs. MAP, which is part of Forge. This tool is easy to use in a production environment at any scale. It is lightweight with a very little overhead and generate a profile of a few megabytes even for large jobs. The profile can be opened afterwards in a user-friendly interface, as you can see on the screenshot on the right. The GUI here displays the application activity process for MPI application or per thread for OpenMP in the timeline on top. The color specifies the kind of activity the application performs. It will be displayed in green for computations, orange for IOs, blue for MPI communications, and since version 19.0 of MAP, it will use pink color for sections of code executed by the Python interpreter. The source code in the middle of the GUI is annotated with activity information, so it becomes very easy to understand where execution time is spent and what kind of activity is performed. At the bottom, a summary of the top functions and call stack is also provided to the user in order to identify the bottlenecks easily. So how can you use MAP to profile a code? Let's take an example of a sequential Laplace solver, which will handle an X by NY matrix, as shown with the Python code snippet on the right. This application is run with the command Python, followed by the name of the script. To profile it with MAP, this command just needs to be prefixed with the MAP command. The -- profile argument that you can see enables to run the profiler in non-interactive mode. This means that the profiler runs in the background and outputs a .map file that corresponds to the profiling results. Other arguments can be used, for example, if you want to specify the profiling output file name. Once the .map file is generated, it can be opened in the GUI with a map command followed by the output file name. So here is the profiling result of our initial version of the serial Laplace solver. The main thread activity on top of the GUI shows that about half of the time is spent computing, and the other half is spent in Python interpreter. What does that mean? That a lot of time is spent in the infrastructure handling the computation rather than performing the computation themselves. This is terrible for performance. We see that the loop nest performing the computation has been identified as the bottleneck. But despite the fact that we are using NumPy array structures, a lot of time is spent in the interpreter handling them. The call stack confirms this with many occurrences to array subscript function, in addition to the array multiply or array add functions. Enabling additional CPU metrics from the metrics menu on top of the GUI displays the amount of floating point, integer, and memory accesses over time. We witness how the time spent in the interpreter affects the performance. Accesses to the system memory are predominant here, with 73% average. This indicates non-optimized usage of NumPy data structures by the interpreter. The amount of time spent in integer computation is also surprising, possibly because of inefficient array indexes computation. Floating point computation on our matrix elements are close to 0% of the time spent. So naturally, NumPy has a more efficient way to perform array computation. Here is our compute kernel code using array syntax on the right. The comment sign enables to rewrite implicit loops on the iteration domain, and we will see how this performs on our system. Here is the new profile result, and immediately we notice that most of the time is spent in compute in our bottleneck, in almost no time spent in the Python interpreter. This means that more time is spent in lower level, more efficient code. The stack confirms that we are spending a lot of time in SSE2 intrinsics. In this profile, almost no time is spent in integer computation. As we can expect, a lot of time is spent in floating point operations, 38%. But more specifically, they all correspond to vector operations. Still, we see that the amount of time spent in memory accesses is high, about 91%, which certainly affects performance, as this indicates that we are barely taking advantage of the cache memory. So to overcome this problem, let's rewrite our compute kernel in FORTRAN instead, and NumPy proposes an easy solution to do it. The F2Py module can be used as a compiler to automatically interface your FORTRAN code in Python and produce an external library which can be imported. To get source level profiling information, in map, don't forget the --debug flag to enable debugging information. Here are the major changes brought to our source code. The FORTRAN code looks fairly similar to our previous Python code with array notation. The main change consists in adding a few directives after the variable declarations to specify their in-out status to F2Py. In the Python script, once the module is imported, the function can be called in a straightforward way. And here is the result, profiling results, that shows that we are spending most of the time in our compute kernel again. And you can see that map can display the FORTRAN source code called by our Python scripts. We managed to reduce the amount of time spent in memory accesses, only 52%, increase the amount of floating point operation to 47%, but to the detriment of vector operations, only 28%. When selecting the FORTRAN line corresponding to the bottleneck, we can go further thanks to the breakdown menu window on the right. When line 25 is well vectorized, with 82.5% of the time spent in floating point vector operations, the line 27 underneath only performs scalar floating point operations. The square root operation is probably responsible for this. The compiler chose not to vectorize it for precision reasons. So what if we compile the same FORTRAN code again with the fastMap flag to allow vectorization? And indeed, the new profile shows that line 27 is now vectorized. As a result, all floating point operations performed by the application are now vectorized. So what about multiprocessing applications with Python? In HPC, MPI is a distributed parallel programming standard that implements multiprocessing. There are many implementations available, all providing compiler wrappers as NPI-CC or NPI-FORT to compile parallel applications. In Python, MPI-4Py provides a straightforward interface, as you can see on the right, to send and receive messages. To run MPI-4Py applications, you will need to use a launcher called MPI-run before your Python command. This will distribute the computations on a specified number of processes. How does map profile such application? Well, the MPI-run command just needs to be prefixed with map to generate a result. And here is an example of an MPI-4Py application that runs a matrix product several times. This code is running on a single node with 8 processes as shown on top of the GUI. After the matrices are initialized, their content are sent to the different processes as shown in blue on the main thread activity. And the matrix product is then executed several times. At the end of the execution, a single process matrix product is run. You can see that one process executes the computation in green, when the 7 other processes are waiting for it to finish. This is a typical sign of imbalance. Additional MPI metrics can be displayed in map to understand what is happening. The MPI call duration metrics shows a graph representing minimum, maximum, and average value for all processes. In this case, we see that 7 processes are waiting in MPI finalize for 4.7 seconds, when one process hasn't performed this call yet. Let's focus on the matrix product now. As you can see, the operation is called line 74 and 83 using the dot product function from NumPy. This function actually calls the sgem function from BLAS. In this example, we can see that in the stack that the corresponding function from the OpenBLAS library is executed, and the version corresponding to my hardware, Intel Sandy Bridge. I understand that pip also install OpenBLAS by default when installing the NumPy module. Selecting the matrix product call in the timeline give me more information on the performance of this library. A lot of time is spent in vectorization, 63.1%, and little in memory accesses, 35.8%, which is good. But since I'm using Intel hardware, can I get better performance with Intel MKL library instead? To do this, I will recompile NumPy manually instead of installing the module through pip. Here is the profiling results using Intel MKL. The stack clearly shows that the call to the MKL library, and we can see that it does bring improvements with 93.4% of the time spent in vector operation and only 7.6% in memory accesses. We are really taking advantage of the fastest compute units and the cache memory available on the node. What happens when scaling up on 4 nodes? As we can expect, communications are taking longer between the matrix product calls, and the time spent in MPI communication now correspond to 21% compared to 13% before. But we are not taking advantage of all the resources available, as we have only one process per node here. Fortunately, the MKL can solve this problem easily with a single environment variable MKL num threads. The results now show a different color in lime green. This indicates the multi-threaded or OpenMP sections of code. The single, which of course corresponds to the matrix product from the MKL. The single-threaded matrix initialization at the beginning is still displayed in dark green. Because of this multi-threaded optimization of the compute parts, communication now becomes the main bottleneck with 53.8% of time. So we're reaching the end of this webinar, and we have shown you how to profile HPC Python application with the latest version of ARM-map. We have explained how to analyze results from the profiler and how it can help you optimize your application further by making sure you are using most of the resources available on your system and the most efficient libraries. Python capabilities are endless, and there are many other modules that can make your application faster. It's up to you to try it out now. And to do this, feel free to request a free trial license of our product by visiting our website on developer.arm.com. We've uploaded a handout material on GoToWebinar where you can find the links and pointer to additional resources. The trial license enable all features of the products on all HPC architectures, as well as the DDT debugger and access to our support for the duration of the trial. Thank you very much for your attention, and I hope you have enjoyed this session. We are going to start the Q&A session now, so if you have any question, feel free to ask using the question tab of GoToWebinar. So a few questions are coming up. The first one is which versions of the Python interpreter are supported? Our tool, ARM-map, supports CPython distributions, including Anaconda, versions 2.7 exactly, and version 3, 3.5 and 3.6. So another question here, which architectures support Python profiling? So all the supported architectures of all the architectures supported by MAP, support the Python profiling feature. You can use this feature on ARM, Power, as well as x86. Someone else is asking, is Python profiling enabled by default in the product? So indeed, it is enabled by default. So our product exists in two different editions, ARM Forge and ARM Forge Professional. And Python profiling can be used on the two editions, of course. So someone else is asking about GPU profiling and can map profile GPU sections along with Python. So indeed, it can. So map can profile GPU code, and if you're profiling such application, you will see a different color appear in the timeline. So the offloaded sections of code on the GPU will appear in purple. And indeed, it works fine with along with Python. You will see exactly the same colors as shown during this webinar. So you will understand which sections of the code are spent in the interpreter, in the multi-threaded code, sorry, or offloaded on the accelerator. I've got another question here. So MPI-4Pi uses MPI thread multiple model by default, and is this supported? So indeed, that's a current limitation of MAP. MPI thread multiple is not supported by MAP, and it will output MAP will output a warning if you are using such programming model. So to prevent these warnings from appearing, you can change the default settings in MPI-4Pi with just a single command, MPI-4Pi.rc threaded equals to false. So that's something that is documented in our user guides. Only single threads or funneled threads MPI model are supported by MAP at the moment. Okay, so these are the only questions. I would like to thank everyone for attending. I hope you have enjoyed this webinar. I would like to apologize for the technical issue we had at the beginning of the session. So if you have any additional question, feel free to get in touch directly. Thanks again. Enjoy the rest of your day.